The simple harmonic oscillator. First, we will remember this problem, simple harmonic oscillator, from a classical point of view. So here we have a block with mass m that is attached to a spring, and it performs simple harmonic oscillations with amplitude a. So x is the distance from the equilibrium position of this block, and there is no friction between the block and the surface. Okay, so for the simple harmonic oscillator, the force that the block with mass m feels is the spring force F, which is equal to minus kx. So if this spring has a spring constant k, then this is basically minus kx. So it's the restoring force. The corresponding potential energy, U, is equal to 1 over 2 kx squared, because the spring force is a conservative force. It has a potential associated with it, which is equal to 1/2 m omega squared. Omega is the angular frequency of the oscillations, x squared, because the angular frequency of the oscillations, omega, is square root of k over m. K divided by the mass. And remember that this comes from the fact that mx double dot mass times acceleration is equal to minus kx, and x double dot is equal to minus omega square x, which is minus k over m x. The corresponding total energy of the block will have a kinetic component and a potential energy component, and the total energy is fixed. It is the maximum possible value of the potential energy, 1/2 ka squared, which is equal to 1 over 2 m omega squared amplitude squared. So what is special about this classical treatment is that it may have any energy, any value of energy is allowed, and it can also have zero energy. So omega equals to 0 is allowed. It may even have zero energy. Now, if you look at this problem from quantum mechanical point of view, let's write down the Schrödinger equation with this potential energy function. So we have the one-dimensional time-independent Schrödinger equation minus h bar square divided by 2m. We have a one-dimensional wave function, so second derivative, ordinary derivative of the wave function with respect to position, dx squared, plus the potential energy, 1 over 2 m omega squared x squared times the wave function psi is equal to energy times psi. So this is the time-independent one-dimensional Schrödinger equation for our simple harmonic oscillator. The ground state solution of this equation, Schrödinger's equation, can be written as psi is equal to b times e to the minus cx squared, where c is equal to mw divided by 2h bar, and the corresponding ground state energy one can show is equal to 1 over 2 h bar times omega, the angular frequency. So we see that the ground state solution for the quantum mechanical simple harmonic oscillator is amplitude b e to the minus mw over 2h bar. So we have mw over 2h bar x squared. So that's the ground state wave function. For excited states, we have energy levels given by n plus 1 over 2 h bar omega, and the ground state energy was 1 over 2 h bar omega, so that's n equals the 0 solution. So n equals 0, 1, 2 is our quantum number. It's an integer value, and you can see that the spacing between the energy levels, delta E, will be, for example, n equals 0 is h bar omega over 2, n equals 1 is 3/2 h bar omega, which means that energy spacing is h bar omega. So energy levels are separated by h bar omega. Okay, so we can see that the levels are equally spaced with separation h bar omega. So we have ground state energy 1/2 h bar omega, 3/2 h bar omega, 5/2, etc. These are the excited states, and the spacing between the energy levels is h bar omega. That's delta E. And so this basically continuous curve is the classical solution, and this is basically the quantum solution. And we can see that energy levels are quantized, and E is equal to 0 is not allowed. But in the classical case, E equals to 0 is allowed, and energy is a continuous variable, so it may have any value. So even values between 1/2 an h bar omega and 3/2 h bar omega, it may have a value here that would be allowed classically, but quantum mechanically, this is not allowed. So we have taken a brief look at the simple harmonic oscillator, classical and quantum mechanical solutions. Classical solution tells us that under the application of this restoring force, F equals minus kx, the corresponding potential energy function 1/2 kx square is 1/2 m omega square x square, recognizing omega angular frequency to be square root k over m from the equation of motion x double dot equals minus omega square x. And the total energy is 1/2 ka square, which is 1/2 m omega square a square. Any value of energy is allowed, including zero energy. Quantum mechanically, when we substitute this potential energy to Schrödinger's equation, we obtain minus h bar square over 2m, second derivative of the wave function with respect to position, plus the potential energy times psi is energy times psi. The ground state solution is b times e to the minus cx square. It's a Gaussian, and here we have c is equal to mw over 2h bar, and the corresponding ground state energy is h bar over 2. The excited state energies are spaced by h bar omega, and so they are changing in units of h bar omega. N plus 1/2 h bar omega is the energy level corresponding to n value between 0 and infinity, and can only take integer values. And you can see that here energy is not continuous as in the classical case. It has discrete values, and zero energy is not allowed.